This is Lab 3, Orbital Motion Lab. There's two parts to this lab. The first part is determining the mass of a black hole with a planet orbiting around it. The second part is to determine the velocity required of a spaceship to launch from a moon and be affected by both a planet and the moon and not crash into the moon. The physics used in this lab are the law of gravitation, Newton's second law, and centripetal force. And the tools I used was GlowScript, which uses VPython to code everything. And the purpose of this lab is to first determine the mass of an unknown black hole using star trajectory data, and second, simulating a spaceship orbit around a planet and moon system without crashing, ideally in a figure 8 pattern. And the outcome for the mass was 1.5 times 10 to the 34 kilograms, and the outcome of the velocity was 3.4 times 10 to the 4 kilograms, or meters per second. The star black hole system. So the star orbits a black hole of unknown mass, and the star mass is given, which is 2 times 10 to the 30 kilograms. My goal is to find the mass of the black hole using the data, and the time step was 1 Earth day. So to do this, I averaged each mass that was updated in the while loop and got 1.5 times 10 to the 34 kilograms. And the code you can see here is of actually that loop. So the picture on the right has all my values for the velocity, momentum, and delta velocity, delta momentum, and then the F net, which equals dp dt. And then the bottom picture is of the calculating the mass of the black hole. So the method was I computed the net force of the star, which is equal to the mass of the star times the velocity, the change in velocity, and I assume the force is due only to the black hole, which is gravity equals g times mass of the black hole times mass of the star, all divided by r squared. And so when I solved for MBH, mass of black hole, I got the force of the net force times radius squared divided by g times the mass of the star. And the code below is the same code as the last slide. So the results, average mass of black hole was 1.5 times 10 to the 34 kilograms. And on the right, you can see the final picture with the 3 arrows that represent the forces. And then the 3 pictures below are of how I averaged the mass. So what does it mean? How does the net force and its parallel and perpendicular components differ from the rate of change of momentum and its parallel and perpendicular components? Well, the net force represents the total influence acting on the star at any moment, while the rate of change of momentum shows how the star's motion actually responds to that force. The parallel component of the force changes the star's speed, while the perpendicular component changes its direction. Part 2, the planet-moon spaceship system. So with a planet at the origin and a moon orbiting the planet, you launch a spaceship on the moon's surface, and the goal is for the spaceship to orbit both the planet and the moon without hitting the moon. And I use Newton's second law to update motion. So as you can see, the moon's orbital period was about 64 hours, and the calculations were finished after 700 hours. The forces on the moon were the force of the planet and the force of the ship, and the forces on the ship were the force of the planet and the force of the moon. And net force was calculated with the change in acceleration, which was calculated with the change in velocity, which was calculated with the change in position. And as you can see here, the x component of the ship speed was negative 2,400 meters per second, and the y was moon speed plus 9,500 meters per second. And the ship velocity total was the vector of those two components. So the results was a speed of 3.4 times 10 to the 4 meters per second, and the outcome was a stable figure 8 orbit around the moon and planet with no collisions detected after 700 hours. I found the initial velocity by combining both its x and y component, giving that total speed, and I added the 9,500 to the y component of the speed because it improved the results. But what if you wanted to predict the motion of the entire system, and what would you need to include in your computational model? Well, with the full system and with many gravitational interactions, we need to include every one of those interactions between all the objects. And the black hole and star would dominate the motion due to their large masses, and the smaller bodies would experience complex orbits, which would turn the system pretty chaotic, requiring lots of modeling. Sources of error were numerical approximation errors due to finite time step, which was 60 seconds, rounding and floating point precision limits in the GlowScript computations, simplifying 2-body and 3-body interactions, and then visual limitations, trail overlap, and scaling, which distort the perception of distance. And thanks for watching.